online workshop. All of you welcome for this online workshop, especially our department faculties members, our HOD sir, our faculty members, and PG Extension Center staff members, and all other research scholars of our department, and PG Extension Center scholars, our PG department MSc and MCA students, and our beloved research scholars, PhD scholars, MPhil scholars. All of you welcome to all. Today, the topic is COVID X-rays image analysis using computer vision. Our resource person, Mr. Srinivas Atreya, he was this very well-known person for 23 years experience among this information management and advanced analytics throughout India and United Kingdom and United States of America. He was started the career in the year 1997. Tata Consultancy Services (TCS) is the destination is project lead, and then it will be started for Wipro Technologies and practice lead analytics. Accenture in vice president next generation architecture. Call Health, the healthcare startup as a destination is analytics head, and Value Labs is the vice president consulting, and then now the presenting post is chief data scientist in Round Square. So the lot of experience among this that area of data scientist, that is artificial intelligence, all the areas. Very good morning, sir. Now take over the sessions. Thank you, sir.
Hey, thanks, guys. Thanks for the introduction, and thanks for inviting me and for joining in on a Saturday morning. Okay, so I'll try and present my screen, and we'll try and do this. Okay. So can you guys see my screen first?
Yes, sir. Yes, sir. Fine.
Okay, fantastic. So yeah, like sir was mentioning, I kind of run a startup right now, and we work with AI and machine learning, more specifically in the areas of computer vision and things like that. So this is a part of work that we are doing with the hospital chain here in the city of Hyderabad. So that's what. So this started off as a research project. Now we kind of also trying to commercialize parts of this and all of it. Yeah. And so today, or the next couple of hours, hopefully, I will just take you through some detail of the work that we did. See, parts of it are IP protected, parts of it I can talk about. So if you have very, very specific questions, I may not be able to give you the complete answer, but I will try to get it as close as I can, because part of it is still pending intellectual property and things like that. But fair enough. So without further ado, let's start. I think my introduction was already given, so I will not spend some time with it, but this is briefly what I have done. I always like to start with a small joke. I will not read it out. I think you guys can read it out for yourself. So hopefully, and I don't really, so most of you, what's your familiarity level? Do you guys understand at least the basics of what is machine learning and things like this? And when you worked, I would assume you'd worked somewhat in this area, because I'm kind of focusing on the work that we've done. It presumes some knowledge, though I will try and explain as much as I can. And in between, if you have questions or something, feel free to ask. Okay, you don't need to wait till the end or anything like that, because I'm not an academician by profession. I'm not a lecturer, so I may not be as good as proper academicians are. Okay, but I will try my level best here. Right. So what are we going to be talking about? So we'll see some approaches of trying to classify COVID and non-COVID sort of patients using just X-ray images. So, the radial X-ray images, how do we do that? We will see a few approaches. We will see some failures and some successes in terms of work that we've done. We will also see a little bit about, given a set of X-rays, can we predict how severe this disease will get over the next time period, because that's something that a lot of doctors have asked us. When patients join, you kind of have their initial x-rays, plus you take it for a couple of days, but then they want to know, is this case going to get severe or not? That helps them plan their emergency services better. So we will kind of see that. We'll also talk a little bit about various techniques that we have used as part of this project, like UMAP, which is actually a short form for Uniform Manifold Approximation Projection. So we'll talk about that technique a little bit. We will also talk about dynamic mode decomposition. That's another technique that we've used as part of doing this. So these are some standard mathematical approaches that are used within machine learning domain. So we'll talk a little bit about it. It's also, I think, equally important to kind of be clear about what we will not, or what I have not prepared to cover today. Of course, I can still answer questions, and if you want to get into these areas, we can talk about it. We're not getting into the mathematical foundations per se of AI/ML. I am also not getting into the moral and ethical aspects of artificial intelligence in healthcare applications. It's a very, very important space. I think there's a lot of research in the world today. But as part of this talk, I'm not getting into that. Probably you guys know by now, I'm not a medical practitioner. So I work with doctors, but I'm not a doctor. So I will not be able to answer medical questions related to COVID. That's not something, that's not my area of expertise. If anybody else feels there's something else I should be talking about, feel free, tell me, and I will try and cover it as I go along. Okay. So what did we set out? See, this project started in the first week of May. Last week of April, first week of May. I work with hospitals in other areas, right? Not necessarily COVID. I do a lot of vision work for them with vascular surgeons trying to understand venous insufficiency, deep vein thrombosis, and diseases like that, but not on the COVID side. Come first week of May, there were some pulmonologists, some doctors who were working at the chest hospital here in Hyderabad. A lot of work had been done already by the Chinese researchers on identifying COVID and non-COVID type of patients, but using CT scans, not X-rays. India being a poorer country, naturally, we do not have as much of CT scans. So we still depend a lot on X-rays. CT scans are expensive in this country. So they wanted to kind of see if there was some work we could do around X-ray based and not CT scan based. So that was the genesis of this work, and it was mostly as a research work, where we also wanted to contribute back to the society. So we said, hey, we will see what skills we have. Let's see if we can do something. So the idea was, given an X-ray of a patient, can we actually classify them into normal, pneumonia, and COVID-19? And probably you realize by now that COVID is actually a form of pneumonia. It's different, but it's very, very similar to pneumonia. And this is the challenge, right? Given an X-ray, it is relatively easy to say if this person kind of has some sort of chest problem, which could be pneumonia, or if he's normal. That's not very difficult. That's actually been done more than a decade ago. Okay. But the challenge is, how do you distinguish between a pneumonia patient and a COVID-19 patient? Now, that's a very, very tricky problem, because in early stages of the disease, both of them look very, very similar. It's very difficult to say if this is pneumonia or if this is actually COVID-19 itself. So this was the challenge. This is where we started in the first week of May. Initially, of course, we don't have too many X-rays, right? By first week of May, we did not have too many COVID X-rays patients within India, or at least within Hyderabad, where I am based out of, where my company is based out of. So anyway, so that's how we started. So what we did initially was we took some of these X-rays from publicly available GitHub repositories, right? So we actually used Linda Wang, Dr. Wang, and Dr. Cohen's GitHub. They were good enough to upload these images in public repositories, which we used. So of course, the normal chest X-rays are easy to get. You know, they're all over Kaggle. If you go over to Kaggle, you'll get that. Yeah, was there a question or something? Okay. So if you actually get there, so normal X-rays is not a problem. We got about 162 normal X-rays, about 159, 160 odd pneumonia patients, and about 117 odd COVID patient X-rays. And these are all radial X-ray images. So I think if you kind of know, an X-ray image can be seen either longitudinally or radially. These are just radial. So one way to think about it is radial is how you normally see X-ray, when you put it against up a light source and you kind of look at it. That's just the radial slice. Anyway, so that's what we took, and that's how this project actually started. Okay, so before we move on, there is a little bit of background that I kind of need to give you. So if you think about it, if you kind of work in this area of machine learning and classification, this looks like a classification problem initially, right? You have to classify. There are 3 different classes. Given an X-ray, you need to classify one sort of a thing. So traditionally, if you kind of look at a problem like that, there are 2 ways to do this, right? Either you use traditional machine learning methods, classifiers. It could be anything from a logistic regression to a decision tree to a support vector machine type approaches. Each one of these approaches, you got to extract the features and then make sense of the features and then feed it to one of these algorithms, and hopefully they will undergo some classification. Or the other way to do that, which is more popular nowadays, I guess, is the whole neural network way, right? So you feed an image, the feature extraction is kind of done automatically, because these things are representational learning, right? They figure out what is the best way to represent that space in a higher dimension to kind of classify. So you have the machine learning ways and you have the neural network ways and things like that. And I will talk a little bit later about how some of those things were tried but did not really work out in this particular problem. Like I said, specifically classifying between pneumonia and COVID-19 is a tricky problem. So we finally ended up using a more mathematical approach, which is actually in the class of a dimensionality reduction technique. It's called UMAP, and I'll talk a little bit about it because this is not very commonly used. A lot of people don't really know. And tell me, see, I don't know. Tell me if you guys already know about this, and if you guys are familiar with what is UMAP and how UMAP or TSNE works, then I can probably skip some of this, or maybe I need to get into more detail. So just let me know as I'm talking through it, right? Yeah, so UMAP, it stands for Unified Manifold Approximation Projection. We will hopefully understand those terms better when I'm done with this. Is a dimensionality reduction technique. And again, I'm hoping there is some understanding of what is a dimensionality reduction technique, but I will very quickly go through it. So one of the problems that we all have in machine learning, or any type of statistical learning actually, is the fact that that most of the data we get is very high dimensional in nature, right? So for example, if you look at an image, okay, if you look at an image that, let's say, a 640 by a 480 image, right? A simple resolution, a 640 by a 480 sort of a resolution, that's still about 25,000 pixels, correct? So when you kind of multiply it, it's about 25,000 pixels. So you can think, if you take each pixel value, right? So each pixel value can be a number between 0 and 255. That's because it's 1 bit, 2 power 8, 0 to 7, right? 2 power 0 to 2 power 7. So that's basically your entire thing. 128. So you give it from 0 to 255. So the values range from 0 to 255. And and each of those pixels can be considered a dimension, then you have a 25,000 dimensional image, right? Even a normal image. If you talk about a 4K image, which is 4,000 pixels by 4,000 pixels, which is HD, right? 4K. So if you're talking about HD type imagery, then you already get into 16 million pixels. That is 16 million dimensions. So, so as you can see, those are huge dimensional spaces in which we have to work in. And you and I, unfortunately or fortunately, can only understand three-dimensional space. We live in three-dimensional space. We understand three-dimensional space. In high-dimensional spaces, there are distances work a little differently. There are a lot of problems in high-dimensional spaces. I will not get into that, but basically your Euclidean distance definition does not work if you get into high-dimensional spaces. So the challenge is you got to reduce the dimensionality. You got to bring and of course, if you want to visualize something, you have to bring it down to 2 or 3 dimensions, because otherwise we can't see anything. At most, we can visualize something in 3-dimensional space, right? You can't visualize anything in 4-dimensional space, and definitely not in 25,000 or 16 million dimensions. There is no question of visualizing anything. So you will have to bring it down. One, to visualize. Second, to even work on it. It becomes a lot easy when it's in a lower dimensional space. So there's a whole amount of literature there. You know, we can. I don't think we have the time to get into dimensionality reduction itself, but that's something you can go through. And this is a one-dimensionality reduction technique. Along with, probably people have heard PCA, right? Principal component analysis and things like that. So those are all matrix factorization type dimensionality reduction methods, and this is more about graph neighborhood sort of methods, right? Where we talk about it. Right. So it's a dimensionality reduction technique similar to t-SNE. If you know what t-SNE is, then it helps. If you don't know, forget about it. We don't have to learn about t-SNE too, because t-SNE is a very, very popular dimensionality reduction technique. That's why I kind of tried to compare it. But if you know about it, fair enough. If you don't know, then don't worry about it. We don't have to know that. So the key components of UMAP, as we kind of do, are topological data analysis. Again, we will touch these things. I want to understand your level of experience with some of these things, so that will tell me how deep I need to go when I'm explaining some of these things, because they can get pretty deep. So topological data analysis, there is some amount of Riemannian geometry, but not too much. And then some fuzzy logic and some complex math. We're not going to get into that very complex math, because that's very tricky. That's even I don't understand. I also don't understand all of that complex math that goes into it. I understand parts of it, but not everything. Okay, so let's get into UMAP. Before we talk about UMAP, it's important to talk about topology a little bit. What is topology? Do people understand what is topology at a fundamental level? Do you understand what it is, or should I get into some detail about it? Okay, so I will briefly try and explain what is topology, and maybe you guys can stop me if I'm going too much or too low or whatever, because I don't necessarily understand what it is. So topology is the study of shapes. Okay, so it's very simple, right? It's formed of two root words, topos and logos. Topos is shape, logos is knowledge. Right. See, that's why it's biology, bios logos, knowledge of the world. So logos just means physiology, everything. You know, physios, knowledge of the physios is physiology. Logos is the same root word. It's a Latin root word. It just means knowledge. So topology means topos is shape, logos is knowledge, and that's what you're studying. So what is topology? How is it different from geometry, right? You would say, well, in geometry too, we study shapes. Yes, you do. But there's a difference between shapes as we understand it in normal geometry and in topology. In topology, we are interested in shapes that can be made from continuous deformation of a shape. Because here, if you see, there is a coffee cup. And it is possible to deform the coffee cup into a donut. Because just by pushing and shoving, you can make it into a donut shape, right? So in the study of topology, when we study topology, a coffee cup shape and a donut are the same to us. We consider both of these shapes to be homomorphic or similar. And the reason we say that is because continuous deformation gets you from one to another. That means you don't need to cut. As long as you don't need to cut or shear something or tear something, you are okay. As long as just any continuous deformation from one shape to another, it is they are considered the same shape. They are considered homeomorphic. Okay, so that's the whole. I don't know. It is a 1 million foot view of topology. There's a lot more in topology as we get along, and we will see. And topology forms a very, very important part of machine learning, at least on the unsupervised side of it when you're trying to understand data. And also what we understand, one other way to think about it is a study of holes. If you look at a coffee cup and a donut, both have one hole. I'm giving you a crude intuition here. It's not absolutely correct, but we don't have to worry about it at this level. So it's a study of holes. The number of different holes in an object somehow determines its shape. Okay, so that's what this is. The modern study probably started in the early 20th century, but this has been studied by ancient Greeks too. So that's a brief idea of what topology is, and we will use these concepts as we build on the concept of UMAP, and then we will see how UMAP helps us classify X-rays. Right. Let's talk about the simplest explanation here of how UMAP works. We will get into a little more detail. So basically, it's a construction of a graph in high dimension. So if you kind of look at any data set, right? Finally, any data set can be represented as points in some space. For example, if you take a normal Cartesian coordinates, right? So your XY plane, every point has basically two coordinates, right? X and Y. That's just two-dimensional space. That's just Cartesian space. So you can add X, Y, Z, and it becomes three-dimensional space, and you can have X, Y, Z coordinates. For example, if a point is in 25,000 dimensional space, what it basically means is every point in that space has 25,000 coordinates. Right. So, and this is a technique that we typically work in high dimensional spaces. So construction of a graph, firstly take all those points, which could be an image, which could be a piece of text, which could be anything. It doesn't matter. It's some high dimensional object. So you kind of draw out a graph, and then the way UMAP works, the dimensionality reduction, is basically to find a graph in some lower dimensions, which is as close as possible to the graph that we drew in the higher dimension. That's the whole purpose, right? You kind of draw a graph in 25,000 dimensions, and then you want to try and see, I don't know, a graph in three-dimensional space, which is closest to that 25-dimensional space graph. So how do you do that? Yeah, there's a lot of math involved, but we'll go briefly into that, but we'll see. So it's to find these two graphs and to optimize it. So when I say optimize, it's basically optimize the distance between them, the distance metric, so that both of those graphs, when they're very, very similar, the distance will be minimum, right? In fact, here we don't talk about distance, we talk about divergence, but we'll get there in a second. Is this making sense to people? Firstly, I don't know. Am I going too high? Am I going too low? Should I? Okay. So that's kind of the technique. In order to achieve this, it relies on principles of algebraic topology and Riemannian geometry. We will not get into too much detail of that, but we'll talk a little bit about each one of those. So I said the way it does it is it kind of uses some sort of divergence metric. Now, what's the difference between divergence and distance? At least in mathematics, the way we kind of differentiate that is distance is a symmetric metric, which basically means the distance between A and B is same as the distance between B and A. Right? the distance is same. Divergence is an asymmetric or an asymmetric metric. The divergence between A and B does not equal the divergence between B and A. It may not make a lot of sense to you when in our normal world we don't see the world like that. But when we get to Riemannian geometry and people who have some understanding of what is a Hilbert space and what is the concept of a metric in a Hilbert space will probably appreciate this. We talk about divergence. We don't necessarily talk about a distance metric. But anyway, so essentially it uses a metric. Teesney actually uses something called KL divergence, which is Kullberg. You can actually check it out. I don't think I'm getting into the details of what is KL divergence right now, but it is a measure of the entropy between two functions. Okay, so you can kind of go look up what is KL divergence, whereas UMAP uses the binary cross entropy measure, okay, which is a little bit different. But anyway, so the principles are relatively simple. UMAP constructs a weighted graph from high dimensional data with edge strength. So the edges of the graph representing how close a point is to another, and then projects this. In order to construct the initial high dimensional graph, UMAP really relies on something called, which is a check complex. We will see what the check complex is. It's basically nothing but a combination of simplicial complexes. So and I'll talk a little bit about a simplicial complex in the next slide and see how that whole thing works. Don't worry too much about a check complex. I needed to say that because that's kind of the mathematical word, and it'll be unfair if I don't say that while I'm talking about UMAP and things like that. Okay, so what are simplicial complexes? Think about like this. Initially, I said there is some high dimensional space on which all of these points are existing, which we cannot see. It is some 10,000, 100, whatever, some X high dimensional space that none of us can see. Now, the purpose is to create a graph in this high dimensional space. So how do you create a graph in this extremely high dimensional space? How do you actually do that? The way is using something called simplicial complexes. Okay, what this is we talk about some simple constructions. A zero complex is just a point. A one simplex is just a line. A two simplex is a triangle. As you can see, it is n-1, right? If there are n points, it's called an n-1 simplex. A three simplex is just a tetrahedron. It's got 4 points. You're trying to join 4 points. It's just a tetra. And then similarly, four simplex, 5. But we typically don't use simplexes of higher order. The question is, can you combine these simplices in a way that can approximate the high dimensional manifold, okay, where the points actually live? That's the whole point. The whole point is, can you combine these 3, 2, 1, and 0 simplices? Forget the 0 simplex. It's actually trivial. It's just a point. Okay, we've just said it because it needs to be mentioned, but you don't need to really bother yourself with the 0 simplex. That's just trivial. That's just a point. But using a tetrahedron and a triangle, so you can fit 2 tetrahedrons right on their base, and you can fit a kind of a triangle on one of its faces. And again, so can you keep doing this to build a manifold, to build an approximation to the high dimensional manifold? Okay, that's how you build a graph. It's called the simplicial graph, a simplicial complex graph of some high dimensional data. And it's a very interesting concept. Mathematically, I think it's been around for 30-40 years now. There's a guy called McInnes, if you're interested. It's McInnes. He's the guy who came up with all of these concepts, and he still teaches, and I think he's from University of Stockholm, if I kind of remember right. So he kind of did a lot of pioneering work on this. It's also called the Rips complex. So again, I'm just telling you these things because after this session, if you really want to understand more about how simplicial complexes are built, to build high dimensional graphs, you should look up something called RIPS complex, RIPS. There are a lot of beautiful videos on YouTube that actually explain some of these things very, very clearly. But as of this talk, I'm just giving you the building blocks of how UMAP is built, not the absolute nth level of detail, because that itself will be a semester's worth of course if you really want to understand everything about simplicial complexes and everything. And I'm sure you guys are all, I think you're all in masters or your faculty members, so somewhere in your academics you might have some of these things. I'm out of touch with academics, to be honest. It's been very, very long since I've gone to a college, so I don't really remember much about that there. So for example, how does this work for real data, right? So let's imagine this is some real data, some real points out there. The blue points representing one class and the green points representing one class. And of course, we have drawn it in two-dimensional space because that's the only thing we can visualize. But you can imagine this to be in any dimensional space. So how do you draw this high dimensional graph or the simplicial complex, this approximation? Okay. So think about it like this. There are all these points, and in any graph-based dimensionality reduction technique that we have, like TSNE or UMAP, you basically look at the neighborhood of points. You see how close is a point to other point. One more thing I forgot to tell you when I was telling you topology. Maybe it's not very important, but I still need to, for the sake of completeness, say this. The topology of a surface is defined as the set of all open sets on the surface. So what is an open set? An open set, actually it's defined very tautologically in that sense. An open set is defined as the topology of a set. So both of them are defined one way or the other, but one way to simply understand an open set is a set of, you think about it like a unit ball or something, right? An unit ball where all the points are within the unit ball. So there is nothing on the surface. So that is an example of an open set. It's a very loose definition. There are many other things that you got to take care of, but you got to think about like that. So the set of all open sets of a given surface can be defined as the topology of the particular surface. So if you kind of look at this, and this is some surface and some dimensional space, and it's lying out there. You have two parameters down below. I've given extent, and I've given something called n_nearest. What do they mean? The extent basically means the radius of those open balls. When I'm trying to get neighborhoods, I'm going to draw neighborhoods, with each point as the center of the circle, and then keep increasing the circle to see more and more. And wherever those two circles kind of intersect, I will kind of call those 2 points as neighbors. And here, what do I mean by n nearest? So each point will try and figure out 5 of its closest neighbors. So that's all that number means. It can be any number. It can be from 1 to 2 to 5 to 500. Okay, there is no you can kind of move it. This is just to tell you how a graph is actually drawn. So you take those points and you basically start drawing those unit spheres, right, or unit circles, centering each one of those, and then see. For example, here, even at 10%. See here, this is not a number. This has to be taken as a percentage of the surface. The entire area is not a right word, but the entire area enclosed by the surface. So for now, think of it as a number itself. Doesn't matter in the understanding, but it should actually be taken in percentage, but that's fine. So for example, here, these two circles collide, so there is an edge between these two. So that's how you keep, wherever they collide, you're going to keep drawing edges between them. That's how you will actually draw the graph. Okay, so as you keep increasing it, you will get more and more. And then how do you join them? These become complexes, right? Simplicial complexes. So that's how you keep adding those complex after complex after complex, and then you start getting a structure to the data. This is how the high dimensional graph in UMAP is dropped. Okay, you're kind of getting some of them fuzzy, and that just means that when a point has 5 neighbors, for the others, and as you increase the extent, you will get more and more neighbors, but the other ones, it kind of starts drawing in a fuzzy manner. So it's not as confident about those neighbors as the first 5 neighbors. That's because I have put the number here 5. If I change it to 10, it will look for the first 10. If I change it to 3, it will look for the first 3. So these two are the hyperparameters that you can tune. Of course, if you take it up to 100, it will kind of take the whole thing. So everything will become, so every point will become a neighbor of every other point. That is pretty much meaningless, right? See, at 0, no point is a neighbor of any point. At 100, every point is a neighbor of every point. So you'll have to check between these two what makes sense. That's kind of a bit of hyperparameter tuning that you got to do as you're drawing out. And this is a bit of an art than science. From experience, you will kind of understand for what sort of dimensions and for what sort of sparsity levels, what sort of hyperparameters make sense. There is no real formula to say, hey, this is the right formula to draw UMAP. And also, maybe as I'm talking, I remember there's a very interesting package called GUDHI, GUDHI. It is made by a set of French mathematicians. It's completely open sourced. It kind of does this plus a lot of other work. So if you're really interested in topological data analysis and UMAP and things like that, you should check out that package. It's completely free, completely open sourced. It's got both C++ and Python bindings, so you can do all of the fun stuff with it. Yeah, so you can go ahead and do all of it. All right, so yeah, you keep going. I think you've got the idea, right? So that's kind of the graph that you will get, the high dimensional graph. The point, of course, is that, see, some of these, so already you can see that there are some cluster type things forming, and there is no connection between this and this. This is a problem. This is a problem, which we will see how to kind of handle. But this is a problem. So you may have to tweak the n nearest type of metric to make sure, because these two are not connected at all. Ideally, you would want the clusters to be somehow connected. So, and as you can see, the other thing that becomes obvious is there is a global structure and there is a local structure, right? So if you kind of...
Srinivas, sir?
Yeah.
In chart window, one questions are asking for one scholar. Sir, 0 and 100, both extremes does not make sense. Then which extent will be better? How to choose, sir?
Yeah, exactly. So, like I said, there is no formula to do that. Okay. So it is from experience, but largely what we kind of do in situations like that is you kind of take an extent close to 50 and you see how many unconnected points like this are there. For example, unconnected clusters. Visualize it in some low dimensional space, 2 or 3, and kind of see. And if this is unconnected, so basically change the extent, change it to 60 or 80 now, and you will see that this will kind of connect. If you change it to 80, this will connect, right? A little bit more, 76, 77, this will connect. So make sure that there are no unconnected clusters. That's the whole thing. And there is no formula for this. You just have to play around with that and then see. Typically, the answer will lie between 40 and 60. Typically. Those are the values under which this will come out to be right, but it is not a given thing. So you try somewhere to 50 and then play around and then see where you get the best result. Does that help? Does that help?
Okay. Okay, sir. Fine, sir.
Okay. Thank you. Okay, where was I? Sorry, I forgot. Okay, so that's what it is. So this is just how you draw the graph. Again, a bit of t-SNE and UMAP. That's just for people to understand t-SNE. UMAP is a replacement. Today, in a lot of high dimensional spaces, at least in healthcare, we are no longer using t-SNE. At least I personally use UMAP only. There are some mathematical changes, but forget the mathematical changes. More from a reality, from a practical perspective, the two things is UMAP is a lot quicker than t-SNE. Okay, so I don't know if you guys have worked with T-SNE, if even with MNIST data, right? You're all familiar with MNIST data, that's 0 to 10, those 10 digits, MNIST data. Even with MNIST data, if you kind of run any T-SNE implementation that comes default with your scikit-learn Python package, it will probably take you around 45 minutes, which is, those are small images, right? 28 by 28, just 784 pixels. So even that will take you close to 45 minutes to an hour. And this I'm saying with a GPU on it. So, and then if you kind of run UMAP on it, it will take you less than 2 to 3 minutes. So there is a dramatic improvement in speed as compared to, and UMAP can preserve more global structure than T-SNE. What does that mean? So basically, if you kind of cluster things using UMAP, and if you do the same thing using T-SNE, both will get the clusters more or less right. Okay, both will kind of get the clusters more or less right. But the global structure, for example, if you look at just the shape of digits, if you just look at the shape of digits, 6 is probably closer to 8 than 6 is to 1, right, in terms of shape. So if you're creating these clusters with T-SNE and UMAP, you will actually expect that the cluster containing the number 6 should be closer to the cluster containing the number 8 than to the cluster containing the number 1. But in T-SNE, you will see that is not true. The global structure is not preserved. The global distances, there is no sense to them. You cannot say that because a cluster is closer to another cluster, you cannot say that they are more similar if you draw a T-SNE. But if you draw a UMAP, you can. It preserves the global structure, not 100%, but a lot better than what T-SNE does. And of course, the reasons there are multi. The fundamental reason is because of the optimization distance metric that it uses. Instead of KL divergence, it uses the binary cross entropy, which kind of preserves. And why does that do it? That we have to get into a lot of math again. But it kind of uses that. And UMAP can run on raw data. So if you actually look at something like T-SNE, you can't feed raw image data to T-SNE, right? You have to do some sort of principal component analysis type thing. You have to get those orthogonal principal components and then feed it to T-SNE, which will reduce the dimensionality even further. It cannot work directly on raw data, whereas your UMAP, you don't need to do anything. Your raw image data or raw text data or raw any data will directly work with UMAP. Just excuse me a second. I'll just get some water and come. Yeah, just excuse me 1 second. Yeah, I'm back. Sorry about that. Yeah. My throat got a little parched. Yeah, so this again, some more detail. We'll not get into a lot of detail on this, but the nearest neighbors, this is important, will affect the influence given to global versus local. Minimum distance will affect how compactly. So if you have more and more and more nearest numbers, if you increase the size, the cluster will become more and more densely packed, because naturally, right, you're basically saying take the 10 or take 100 or whatever. So it will consider all of them to be its closest neighbors. So the more and more you can, yeah.
Sir, in your window, alert message window is there. Hide this.
Which this one?
Yes.
Okay.
Yes, sir. Yes.
Is that fine now? Yeah. Okay. Yeah. Where was I? Okay. So the minimum distance will actually kind of affect how compactly packed the local parts. So if you increase the minimum distance parameter too much, what will happen is you will not be able to see the individual points that clearly. So it will be more tightly packed. So the local structure will be given weightage rather than the global structure. It's always a balance between how much global structure do you want to preserve and how much local structure you want to preserve. And that depends on the problem that you're talking about. For example, in this COVID X-ray problem that we are talking about, local structure is way more important. See, I am not really interested in understanding how different is pneumonia from COVID. If I was interested in understanding that, if I was more interested in understanding how different a cluster is from another cluster, I will actually try and preserve the global structure more. Right now, my thing more or less is I want to understand whether this belongs to this cluster or not. So the local structure is somehow more important to me as part of this problem, but it's not always the case. In a lot of business applications, where you're trying to do customer segmentation, you do things like that, global structure becomes more important. So we then preserve the global, but that's use case based. That's based on how you want to deal with some of these things. Yeah. So why is it faster? It's fundamentally faster because there is no normalization step. So in TSNE, what it does is the way it calculates the distance. Firstly, TSNE uses Euclidean distance. Okay, so it uses Euclidean distance, whereas this uses a combination of Mahalanobis and Manhattan distances. But that's not just the thing. So distance between 2 points in TSNE is calculated by the distance divided by the normalized distance across all the other points. So it is normalized, and that normalization takes a lot of time. Especially you're talking about high dimensional spaces, you have to calculate the distance for all those 1,000 points across 1,000 dimensions. So that kind of slows down the computation. So that's one reason why the speed is there. Then in UMAP, the other important thing again is the actual optimization algorithm itself, which is, like I said, it's a binary cross entropy. Binary cross entropy is not a very difficult algorithm. We all use it every day in our lives. But the implementation in UMAP is a multi-threaded implementation. At least what comes up if you actually use the package that Mechanis gave us, which is actually, you can just do pip install python -umap. Okay, it's a package that Mechanis has developed. That package has that particular cross entropy algorithm written in a multi-threaded way, so it is much more faster than your component, your KL divergence piece in TSNE. Okay, so that's and the reason I'm saying this is because there's so much work people do in TSNE over the last 10 years or so. So that's the only thing. So is it always great? No, it is not really that great, right? Because if you look at this, if you kind of look at this sort of structure, and if you look at what TSNE is giving you and what UMAP is giving you, TSNE is probably giving you a better result to this than UMAP. UMAP is completely confused. It's not giving you a good result. So that tells you one more thing. If your classes are mixed such that one class is much sparser than the other, then typically UMAP struggles. Okay, so that's also an important point that you have to realize. So for example, you see very few blue points, maybe 1 or 2, surrounded by a lot of orange points. And if you try and do something like that with UMAP, UMAP will not be able to understand that difference. Okay, it will start throwing up blue and orange everywhere, and which is not really right. Maybe the TSNE at higher values of perplexity is giving us better values. Okay, so that's something you got to understand when you are dealing with data sets. For example, if I had only 10 COVID examples and 1,000 normal pneumonia X-rays, UMAP based clustering would not have worked for me, okay, or it would have given me worse results than probably much simpler dimensionality reduction techniques. So it's definitely quicker, but doesn't mean that it will always work better. And this is important. And this link, anyway, I'm going to share this PPT with you guys. When you have some time, go over this link. This probably has a good explanation of this rather than what I am talking about. So you want to get more detail, there is a lot more detail here. No, it's not all hype. It works well for complex data sets. For example, again, this is a very, very standard example that people give. This is the when the original data is in the shape of a mammoth skeleton, right, which is like a big elephant skeleton. So if you do a t-SNE projection and a UMAP projection, the UMAP projection definitely looks a lot better, a little more like that mammoth skeleton than the t-SNE projection. So more complex data sets where the shapes are extremely complicated, UMAP tends to be much faster and give better results. But where data sets are very, very, they're not balanced data sets, there's extreme imbalance, and one class is surrounded by another class and things like that, what we call the clean bottle shape, right? If the data is in a clean bottle shape type of problems, then UMAP does not always work very well. And the speed is very, very obvious, right? The speed is brilliant. It is much, much faster. And a lot of times it's not even tractable. Your t-SNE is not even tractable. If you have hundreds of thousands of images, and if you run something like t-SNE, it will not come back for weeks together. So it's not even tractable at that level, whereas UMAP is definitely way more tractable. So that kind of makes some sense. Okay. So coming back, so this was a little detour on what was UMAP. Hopefully there is some idea on what is UMAP. So how did we try and do this? We tried solving this problem in 3 different ways. We initially wanted to write a simple neural network, a simple convolutional neural network, to try and see if we can actually classify those 3 classes. We tried everything. We tried starting from VGG type architectures all the way to DenseNet 121 type architecture. So all the way, the Retina nets, the ResNets, the Inception, all of those convolutional neural network architectures that we tried. Then we tried UMAP as a data transformer, basically meaning you run the UMAP, take representation of each point as a feature, and then try and run it through the more classical classifiers like your decision trees and vector machines and things like that. And the third approach that we tried was really something called metric learning with UMAP. So I'll actually make it learn the distance metric. So it's kind of supervised UMAP. So right now we were doing unsupervised UMAP. But let us say if you tell them that this point and this point is actually closer, because you're now saying that both of these points belong to the same class, can it then learn the local structure better? So it's supervised learning with UMAP was the third thing that we tried. So 3 different approaches, and we will quickly go through 3 different approaches that we tried when we did this. So when we actually did with neural networks, it was funny. Okay, we were getting high accuracies. We were getting accuracies in the range of 97, 98. The validation accuracy was also in the same region. So for us, we were very happy. So when we did this, we could not see any potential chances of overfitting and things like that. This was working well. Everything was working good. We were like, okay, fantastic. So we thought the project is done. And then, of course, because this is healthcare, just because there's a good F1 score doesn't mean I can kind of say the work is done. We have to understand what is the model actually learning, right? Because the model can get to the right answer by learning wrong things. I think a lot of, if you're students, you'll probably know it, right? You can sometimes get to the right answer by doing all the wrong steps. So we did some sort of gradient activation, some sort of CAM sort of approach where you wanted to see what was each one of those layers actually learning, and then kind of illuminate it. And you will find it funny that all the COVID negative X-rays that we were seeing were actually learning something about this R. Okay, which to us doesn't make any sense, right? Why is the letter R written on the side of an X-ray has to do anything with what that X-ray was negative or positive or something like that? But apparently, in our example that we had, every single COVID negative X-ray had this R written on the left-hand side. You're seeing left-hand side, so it's actually the right-hand side of the X-ray. So this was written. Why they had written, I don't know, but they had written. And the neural network was just learning that. So it was actually learning nothing useful. It was not classifying based on any of how the X-ray was looking. It was just, so everything that was R, it just said negative. So everything that didn't have R, it was saying positive. And that was that was a movement of yeah, but this sort of things always happens with neural networks, right? And that's why I say, when you get a good result with neural network, always please go back and tell me, what has it actually learned? Are you sure that it is learning the right thing? Because generalization for something like this would have been a nightmare. When I have put it in production, if I had put it in production, then it would be a nightmare. It's if the R is not written, it will just call everything positive. That's all. It doesn't care about anything else. It's not learning anything. Or it's learning something, but it's also learning a lot of wrong things. So, and I think, is this making sense? Because this is a very, very important concept. And I think there is a lot of a myth around in the world today. If you read, there will be a lot of GitHub repositories that will keep saying, we have done COVID X-ray classification, we have done COVID X-ray classification. You take those models, run simple gradient activation on them, and see what exactly are they learning. And then take it to a clinician, and then say, whatever it is learning, is this valid medically, clinically? And most of the time they will tell you, no, it is not. It is just learning some quirk in the X-ray, which is not right. It will not generalize. It has to learn the right thing. And that's a big problem. And that's a big problem with healthcare itself, because a lot of times when we run these neural networks. So anyway, so this went on till June mid or so. We did a lot of work on this, and finally we figured out that this is not really working. So we gave up on this. Like I said, if you remove the pneumonia, if you just give normal and COVID, these things are working. Even then, they're learning some wrong things, but still the generalization is good. The F1 scores are coming in higher 60s and lower 70s, so that's not very bad. So it is coming decent. But if you add the pneumonia into the mix, it's going for a toss. It's not able to do that. So what's the next thing we tried? We tried UMAP as a data transformer. Like I said, you draw the UMAP and then you take the feature descriptor or the pixel descriptor for each one of those. If it's in 1024 dimensions, it's a vector of 1024 numbers. So we tried those UMAP descriptors with all sorts of classifiers, starting from the simplest nearest neighbor KNN type thing to SVM and decision tree and everything. We ran grid searches, of course, to fine-tune the hyperparameters and things like that. So we also played with different number of components, right? So if we did not, because finally it's a dimensionality reduction technique. So how many dimensions do you take? So you could take any number of dimensions, from 10 to 3 to 10, because if you do a t-SNE, you'll take 2 or 3 because that's the only thing. But with UMAP, you can take any number of dimensions. So we've taken all sorts of dimensions. So one of the best results that we got was with SVM when we used a linear, so just a linear SVM, a linear kernel with SVM. At about 30 components, the mean F1 was coming to around 0.72. So it's not bad. The precision and recall were like right up there. Both of them were in higher 70s. So, and the F1 was around 72%. Is there a question from anyone?
Yeah, Mr. Srinivas, I am Professor Tangavil.
Yes, sir.
How are you?
Doing good, sir. Thank you for reaching out. Yeah.
Yeah, actually, now I am on the way to attend a meeting.
Okay, sir.
So I was not able to. I think I am not able to fully attend your session.
No problem, sir.
But here the thing is, you have introduced this UMAP for us. Previously, yeah, we have used a lot of techniques for dimensionality reduction. But I
Yes.
think for me and as well as for our research scholar, this is quite new. And as far as my knowledge goes, no one has applied this UMAP for as a data transformer or
Yes.
dimensionality reduction. Even we have used some rough set concept and other mathematical concepts.
Yeah.
And here this is new to us. But here my doubt is you are actually some of our scholars are using this convolutional neural network for dimensionality reduction. So to say, we can say as downsampling.
Yeah, you can do that, right? Auto encoder, basically run it like an auto encoder.
Yes. Yeah, auto encoder, or some people are using convolutional neural network.
Yeah.
Because these things are coming under machine learning.
Yes,
this
sir.
KNN, SVM, and decision tree are all this machine learning. And also, what my doubt is how to differentiate. Actually, if you give neural network, then it will automatically, if you train the neural network, then automatically it will classify it. So
Yes.
that means whether it is pneumonia or COVID.
Yes.
So is there any, for example, some of my colleagues and myself are working on mammogram. And we know that the early detection of mammogram is our aim is to identify the microcalcification.
Right. Right.
So that is the sign of indication of the breast cancer.
Yeah.
So like that, is there any sign of indication in the
Yes.
X-ray image to identify the pneumonia or COVID?
Yes. There is. See, the one thing we have been able to clinic. It is basically accumulation of fluid on the left-hand side of the
Exactly.
of the error. So it is that fluid is what gets it. The problem, sir, is between pneumonia and COVID, it is practically impossible till it gets very, very severe, at which point classifying doesn't make any sense. And actually, I will tell you little later. See, what really happened was we did all this work. We went to a hospital. Okay, okay, I'll give you. There's no secret. It's like Care Hospital here in Hyderabad. Okay, I was supposed to deploy. When we spoke to the pulmonologist, that guy was saying, "See, there is no point in doing this because end of the day, he's saying between severe pneumonia and COVID, you can only identify when COVID becomes very, very severe. At which point detecting doesn't make any sense because that person will most probably die."
Yeah. That's what I would like to know. How to identify it at an early stage.
That we were not able to do.
Challenging task. That is the challenging task.
Yeah, that we were not able to do, sir. Okay. So finally, what we did was, then the doctor said, "See, the useful thing for me is a patient joins today. Okay, I take his X-ray. I take his X-ray two times a day. They're taking X-ray at Care. Okay, morning and evening for a COVID patient. So what they're saying is, his biggest problem is they want to know if this COVID patient will become severe or not. Will he be requiring ICU bed or not? Is what the hospital wants to know.
Correct.
So so they were saying, looking at some, let us say 4 or 5 X-rays over the last 2 days. Is there a way to predict will this become severe or not?
Yeah.
That was the problem which they finally said they are interested in. Because they said classifying this, see, using X-rays, at least we are not able to do. With CT scan, you can.
Yeah.
But not with X-ray. With X-ray, that early detection between pneumonia and COVID is not coming. They are looking exactly same. Okay. At least me and my team here have not succeeded in that. Okay. Then for the second problem, we used something called dynamic mode decomposition. That method also.
So you have processed CT image also.
Yes, we have processed CT images also, but that I didn't do for an Indian hospital. We are doing it for a Texas-based client. Okay.
Okay.
So for them,
Here the thing is, this healthcare people are not extending their cooperation for us. Once if they give the data, I think we can do certain things.
oh, it is. Don't ask me, sir. See how much trouble I went through. I know. Okay.
Yeah, that's what.
To get
Yeah,
the
here
permission and
also,
care.
if we go and seek the help of people from hospital, they are not giving due respect for us. They are believing. They are not believing us.
No, that is what I will tell you a secret. Okay, at least what worked for me. Maybe it will work for you. I don't know. Okay, so the deal is very simple. You have to go and show them an opportunity to make money.
Yeah.
Okay. See, they are not interested. They will not be interested in any academic thing at all.
Correct. Yeah,
They
they
will
are
not be
interested
interested.
in minting the money.
They are only interested in making money. Okay.
Yes.
So what we have to tell them is, or what I told these fellows is, work with me. I have some contacts in the US. Okay. If we are actually able to do this, we will sell the solution plus the data.
Correct.
Okay. That is the only thing they've signed up. Otherwise, if I tell them I want to do this, that for academic purposes, they won't even pick up the phone, sir. Simple.
Correct.
Unfortunately, India, the world is like that only. US is much better. At least they are actually the best is Italy, sir. Italy and all those fellows are really giving data. If you have research scholars, no, I will send you a few links after this class, after this session. You can ask them to contact them. They will give a lot of data.
Okay.
You can collaborate with them, and even FDA, National Institute of Health, NIH in US also.
Okay.
They are also interested. India, it is very difficult, sir. I'll tell you. They will not give the data.
That's what I'm telling, because they are taking X-ray or CT for a lot of patients. If they could give the images, then we can train the neural network and we can able to make use of the artificial intelligence in the diagnosis of the diseases. But here we are not able to get the support from hospital.
We will not. So you will have to tell them, give them a financial incentive only. Otherwise, like from their perspective, they will say see, even when we go all this, doctor will say, what is the point? See, the doctor will be right only 50% of the time, but he will want the neural net to be right 99% of the time. They get angry when I tell them that, sir, you are also wrong sometimes. It is not like you are 100% right, no?
Correct.
But they will say, no, that cannot doesn't work. Anyway, these are all real problems that you know better than I do. I can tell the technical piece of work. This, if you have to do, then I think let us talk separately. We may have something, but that's a different discussion we need to have.
Yes, sir.
Not like that.
Okay. Thank you. Please carry on, sir.
Yeah. Thank you.
Please.
Yeah.
Hello.
Okay. So where was I? Let me just. Yeah, give me 1 second. I've just lost my chain of thought. Yeah, we also use different distance metrics and all of that. Typically, we use Euclidean. I think all of this everybody knows. I don't want to detail it out, all of that. Of course, some of this is difficult. You also need a lot of GPU access. If you want to run this, something like Mahalanobis distance on huge dimensional data, then the system will largely crash until and unless you have 10 GB, 11 GB type of GPU machines and things like that. So so even when we used UMAP as a data transformer, and even with SVM when we did and plotted this, you are clearly seeing that clusters are not getting separated. Whatever distance metric we use, still it is like, how do you draw? The clusters are not at all clear. They're all over the place. Like I keep saying, that pneumonia and COVID-19 thing is very, very difficult until and unless COVID-19 is in a very advanced stage, in which stage it most probably doesn't make sense to classify it anymore. So again, neural network, the same thing I told you. We did a lot of work. We got some decent results. But like I said, it learned the wrong thing. The generalization was very, very poor. when you're actually putting it on the actual production sort of pipeline and testing it at care, the results were not good. The results were actually worse than a random guesswork. So it was not really working. Metric learning is what, in fact, this diagram is not right. Don't worry about this diagram. This is actually a cluster of many things. What is metric learning? Metric learning basically means it's supervised UMAP. UMAP itself, but you are kind of telling you, instead of saying that these are your neighbors is 5 or 10 or whatever, you are basically saying that, okay, Baba, all of these are your neighbors. So I'm giving it supervision. I'm actually telling that these 10 X-rays are of people with pneumonia. So please cluster them together. So when you do metric learning, when you do supervised learning with UMAP, the clusters get separated very, very well. 3 clusters, you have fantastic separation. If you take it and run it on production data also, performance is a little low because for each one, it still takes about 20-25 seconds. But we got very, very good results. Of course, the problem there was, like I said, the doctors were not really interested in this solution itself. The doctors were saying classification of this, because most of the COVID patient data that we were able to classify anyway were advanced stages of COVID, not early stages of COVID. So they were saying there is no point because that advanced stage of COVID, I already know that he has COVID because a lot of other symptoms. X-rays, we don't diagnose using X-rays, right? Your oxygen, your SpO2 itself will be less than 92, less than 90 and all of that. That plus lung infection automatically tells us that it is COVID. We don't need anything like this. So unfortunately, after about 2.5 months of work, the hospital was not really interested when we took this, right? So when we actually took this to thing, they were not very interested. So the clinical staff just saying X-rays only form one part of diagnosis. For acute cases, even radiologists can easily identify. So not much benefit. The one area where they did ask us to help was saying that if by looking at a patient's X-ray for a couple of days after getting admitted, the AI system can predict if the system will get serious and will need an ICU bed. That will help them plan emergency beds better. So they were saying that is a problem that we are actually interested in solving. So that is, I think, another lesson to anybody getting into this field. The problem that you think you will solve by getting into it is not the problem that anybody is usually interested in. You will have to change the problem, but that's just the way these things work. So that is what we set out to do. This was sometime in July. First week of July or so, we said, okay, we will now try and do this. But for this, as you can understand, we need longitudinal data, right? So we want the same patient's X-ray over a period of time. And then you want to kind of predict how that X-ray will look the next time period so that the radiologist can look at it and say, hey, this looks serious or not. So that was the idea. So again, we tried some time series methods and things like that. They didn't really give us good results on that. I'm not getting into the details of all of those. I think my team tried a few simpler and more complex time series methods and all that. But finally, we set out to use, now this is a method, I come from some fluid dynamics background. At some point in my life, I worked with, now if some of you have worked with fluid dynamics sort of systems, chaotic systems and all of that, probably know Stokes-Napier equations and things like that. So maybe then you may have an idea of what is dynamic mode decomposition because it comes from that field of life. So the idea fundamentally is, without making any assumptions about that data, can you understand what are the modes that are driving the system, right? Because every system evolves in space and time. X-ray also can be seen as a spatio-temporal system in that case, right? Because there are certain parts of the X-ray that get lighter or darker and that evolves over time. So it's a spatio-temporal. So any physical system, you can think about it like, I don't know, any physical system that you can think about is spatio-temporal in nature, typically. It moves through space in time. Of course, we still don't know how to move through time in space, so it has to be moving through space in time. So for any such system, how do you find out the modes, and using the modes, can you generate the system pack? It is very similar to the concept of an autoencoder. Okay, but with time. Think about it like an autoencoder with time, because normally when you do an autoencoder, you are only doing spatial encoding. You are not taking temporal. Here I have to determine how the X-ray will look in the next time period by looking at it over the last 5, 6, or 10 time periods. So it's a spatio-temporal sort of a problem to solve. I hope that's making sense. Normally, if you want to reconstruct the space, just the spatial modes, you will use an autoencoder, right? It will give you the spatial modes of a system, whether it's an image or whatever else that you're talking about. When there is a multi-scale system, it's not always possible to define the function that governs it, right? So when you study physics in high school or even up to bachelor's and all, it's very simple. You are given laws. You are given dx by dt, right? Newton's laws govern how things move. Similarly, in every subject, you're just given those laws and you happily work through them. But then in real life systems, these are multi-scale systems. So it's not working only at one scale. It is, you usually do not have the dx by dt. The dx by dt is not given to you. You don't know the set of governing equations for x dot, right, as spatial movement through time. So how do you do that? So dynamic mode decomposition is one way, where the idea is that you can approximate that with a linear approximation. Where you don't know the equation. Of course, we don't know the governing equation for X-rays. If we knew, then none of this was required. We would just put in the values and we will get how an X-ray looks at any time period. But we don't have the governing equations for an X-ray, and that's why we have to go through all this trouble. So of course in DMD, it is still a linear approximation. So we are just trying to do a linear approximation of the system. So of the form dx by dt is ax. So really think about it like this. Forget the equation for a second. Conceptually, you have a huge matrix, and let us imagine each column of that matrix represents a time period. Okay, and each row of the matrix represents a measurement. So for example, if you're talking about X-rays, then maybe let's say over 10 time periods, over 5 days, somebody has taken longitudinal X-rays. So it basically means that there are 10 columns, and let us say each X-ray is, I don't know, whatever, 1,000 pixels. Then you're looking at 1,000 rows. So it's a column that has 10 columns and 1,000 rows, right? That is you can think about it as the X-ray data, longitudinal for that patient, right? And essentially what you're trying to say here is, let us say it has 10 time periods, then you make a matrix of time periods 0 to 9, and you make another matrix of time 1 to 10, and the second matrix should be some linear multiple of the first matrix. So because that's the whole idea, right? You're kind of saying that the second matrix can be gotten from some linear approximation of the first matrix. So the time period 2 is nothing but time period 1 into something, into a linear vector gives me time period 2. That's what you're kind of hoping. If you can approximate it like that, then you can get the eigenvectors, and the eigenvectors give you the modes, the eigenvalues give you the values of those modes. That's the whole idea behind DMD. It's actually conceptually not that difficult, but it's a very, very interesting concept. And this is the first time I have seen, or at least to my knowledge, we were probably the first guys who applied this to an X-ray analysis. People have used this for years together in fluid mechanics. Fluid mechanics, and to understand things like turbulence over aircraft engines, in airline industry, these things have been used extensively. But as far as I know, we were the first guys to use it as far as the X-ray imaging technology itself was considered. So once again, I think University of Washington, you can look up University of Washington. University of Washington in Seattle does some pioneering work on this. They have some very, very good research scholars and professors who are pioneers in this. The entire dynamic mode decomposition is something that they work on a lot. And to be honest, that's where we got the idea from. That's where, reading those books and those articles is where we also thought this may make some sense. And we were also working here with IIT Hyderabad. IIT Hyderabad, there is a professor who also works a lot on this sort of things. Okay, fair enough. So the algorithm again, of course, you have to compute the SVD, right? Because it's not a symmetric matrix. You're not going to get the inverse and things like that. So you will do the singular value decomposition. You will get the diagonal matrix, and that's all not very complex. So you will take that rank of it that will make it square. So a lot of values below that rank. You just take an SVD and make sure the rank R is equal to N. N is to R, like where it becomes a square matrix. Becomes easy for you to work later on and all that. And if you guys are familiar with MATLAB, this is not very difficult to do at all. It is just a few lines of code, honestly. But the thing to understand is if you run a huge matrix, if you have, let us say, the matrix we had was simple. It was just 10 by some 5,000 or 10,000 sort of rows. So that's a simple. But you have a million by million rows, and if then you run it through something like dynamic mode decomposition on MATLAB and things like that, it wouldn't work. Naturally, it would fail. So you will have to do some reduction, some rank reduction before you kind of get into work like that. So once you get the eigenvalues and eigenvectors of that A matrix or that A slash matrix or whatever, then you start understanding the modes and this is two-dimensional. So it's spatiotemporal, it's both. So that's so if you look at the X-rays, so this is the sort of data that we were getting. So for example, these are longitudinal X-rays for a patient taken over 3 days. So 1, 2, 3. So the idea is looking at these three, can you predict how this X-ray will look in time period 4? Of course, the key thing here is the time period has to be constant. For example, you cannot take this on day 1, this on day 3, and this on day 4. That doesn't work because the difference is not constant, right? If you take it on day 1, this has to be 2 and this has to be 3. So the difference has to be constant. That is it. There are ways you can do dynamic mode decomposition even if the time period is not constant, but that's called extended DMD, eDMD. But we haven't used that. So that's something that also can be done. If you're familiar, it's fine. If you're not familiar, you can just read up, I guess. So essentially, when you kind of do these modes and kind of plot them, those eigenvalues on a two-dimensional plane, this, for example, is the unit circle. Of course, it's not looking like a circle because in the diagram, I think I pulled it around, but this is a unit circle. It's not a unit ellipse. It's a complex circle in the complex plane. So these three red dots, so for example, for these three X-rays, we could get 3 modes. The way you have to understand those modes are, if the mode is within the unit circle, for example, these 2 modes are within the unit circle, they are decaying modes. So modes that are actually decaying in time. So they will get to 0. The mode that is outside the unit circle is essentially the mode that is growing, that is expanding. And if there is a mode on the unit circle itself, in this case we don't have, but if we do have, then that means that mode is neither decaying nor growing. It is going to remain constant. It is typically not found in a lot of physical systems, but because in a lot of physical systems, either things are growing or things are decaying. Things are not remaining constant in most physical systems that we observe. But in man-made systems, you will see modes that are neither growing nor decaying. Those modes are not very helpful, frankly, right? Because you can do nothing with it. Nothing is there, just constant modes. So if you kind of do that, you can reconstruct it for the next time period using the DMD mode. So you will get an X-ray like this which is slightly different, I would presume, from the other 3 X-rays. So the radiologist, right now we are trying to do it for 2 time periods. This sample is only for 1. We have still not succeeded for 2 time periods, honestly. We're still working on that. It decays very, very quickly. So to get the next time period is not that easy. And please remember, we are only talking about a linear approximation, whereas very honestly, processes these like this in nature are not at all linear. They're extremely non-linear. So we will have to use things like Koopman's operator and more sophisticated math to kind of get there. We have not succeeded yet. We are still working on it. Maybe by end of the year, we might be able to get to the Koopman's way of doing it. We're still not there. But this is pretty good. And right now, we are strangely enough, even though we did a lot of work on COVID, right now they're not really using this for COVID. They kind of wanted us to do it for chronic venous insufficiency. That is another venous disease in the legs, and they actually take CT scans and X-rays of legs, and that is where they want to use this before they want to use it for COVID. The hospital is not really interested in using it for COVID at this point, but they have their own reasons. I don't know why. But for us, this is a paper that we have presented in a couple of places. I'm again talking at the MedFocus presentation, October 22nd. I'll probably send you guys a link where I'll get into a lot more detail about this. So this we have presented in a lot of international conferences. There has been some interest from some people. They want to collaborate and things like that. So that is the idea. The idea is you do dynamic mode decomposition, you get the dynamic modes, and then you reconstruct the image using the modes. Of course, the problem is it is a linear approximation. So that's why the accuracy is not that good, okay, at this point. When we are comparing, a lot of times they are saying we are missing some critical components and things like that. So, for example, the aerolas in lungs are not coming out clear. So I don't want to give you the illusion that this is all done and solved. This is still a work in progress, but this is very, very impressive. At least I'm very proud of this because I've never seen anybody do anything like this with DMD. So future work, we have to use the Koopman operator, the nonlinear spatiotemporal. And if any of you have worked with the Koopman operator, you would know that it is computationally extremely complex. You have to get into some sparse regression models like SNV and other things, which we are all still, me and my team of 2 people are still trying to understand and do that. Yeah, we don't have a lot of academic strength, right? We just collaborate with IIT Hyderabad at this point. Guys, that's all that I had really for today. And that's my details if anybody wants to connect or talk to me. I hope this was a decent introduction. And yeah, that's all that I had, guys.
Thank you, sir. Anyone who have asking some question in chat window, any type regarding with the computer vision, regarding with COVID analysis?
Yeah, you can ask me anything. It doesn't need to be only along this talk. Anything else in AI, ML, vision, NLP you want me to ask, please feel free. Anything. And that's okay.
Hello, sir.
Sure. Hi.
Sir, anything to find like error measures like error rate? Is there any measures to find error rate, sir?
Evaluation measures, sir.
Error measures in what?
Sir, in these kind of you are evaluating the extreme, finding the extreme of COVID, no, sir?
Yes.
Okay. Is that 100% true, or there will be some errors?
No, it is definitely. See, normally you do what? Normally you do precision recall type measures, right?
Okay.
So normally you do precision and recall. So Precision is how many of the right things. Recall is how many of the right things are you getting. Precision is how many of the things that you've gotten are right. So you do precision and recall type measures, and you calculate F1 scores. Precision into recall divided by precision plus recall. So, and that's essentially what you kind of do a lot of times. And there are much more sophisticated error measures also, but this is the fundamental parts of it. And then you can get into measures like glue. Yeah. So, but first, I think it's better to start with precision and recall type measures. Those are the fundamental measures that work. I saw some other question also. Somebody else had another question or something. Somebody typed something.
Okay.
No, did that help your question at all, or?
It helped me, sir. I'm just
Okay.
asking.
Thank you. I just want to make sure that I'm answering what you're asking. I think some.
Window.
Yeah, chat window. Let me open the chat window. How do I open my chat window? Let me see. Full screen. Turn on captions. Change light.
Upper screen, sir. There's people. Yeah.
Okay. Chat. Okay. Oh, people are asking. Okay, good. Can you suggest some suitable pre-trained weights, VGG for COVID X-ray data? Suitable, I don't remember, but I think you can just check on Google, you will get them. But I think the best are for DenseNet 121 and some ResNet are available as far as I know. Okay. But again, all of them are available for COVID, non-COVID. None of them is available for COVID, non-COVID and pneumonia. You can just Google it and you will get it. I think for DenseNet and ResNet, they are definitely available. A lot of kids have done so many GitHub repositories now. But the whole problem is it doesn't work for pneumonia, and COVID distinction doesn't work.
One more my question,
okay.
sir.
Yeah, sure.
Say this X-ray is a low precision rate because you compare with any other modality like that CT scan or any other Doppler scan is there.
Yes.
Sir, X-ray is the low density power in your radiation, is the low radiation power.
Yes.
So this is how it is possible to identify this X-rays in the chest X-rays, especially chest X-ray. How to be identification from both either suspicious cases like that pneumonia or other COVID-19 or any other lungs problem? How to be this justification about this the type of suspicious cases?
Yeah, that's actually a good point. See, a lot of value will come from it, doctor. So essentially, that's an anomaly detection problem, right? So
yes,
what you're trying to find out is this is the normal X-ray and this is not a normal X-ray. We don't really care whether it is a COVID or pneumonia or whatever. So it is an anomaly. You should solve it like an anomaly detection problem. So algorithms like isolation forest, for example, is a great algorithm for doing anomaly detection. One class SVM. Okay. If you neural networks will not work that way because see, neural networks, the problem is they use cross entropy largely as the loss, right?
Yes.
With any cross entropy loss, you need to have a standard and with the standard. So it is not an anomaly detection because anomaly means you have one class and the rest of the world is another class.
Sometimes false positive rate should be go to higher, sir.
Yes, exactly. Exactly.
Misdiagnosis. Yeah.
Exactly. And that is the problem with using something. That's why I'm saying if you want to reduce that, it's better to use an anomaly detection approach than a classification approach. So I'm saying use something like isolation forest or something, which does not depend on, it is not trying to classify. It is only trying to learn what is one class. So everything else is different.
Yes.
It is that will help you reduce your false positive type of cases.
You are trained with all the type of COVID-19 X-ray images, sir?
Not all. I can't get access to all, but whatever I've gotten, I have done. Because see, like Dr. Thangavel was also talking, it's very difficult to get access. Okay?
Yes.
Hospitals are not willing, and you need consent from patient also.
Yes.
So, see, most people don't understand. So if you go to them, they will say no.
Yes.
So it is very, very difficult. If I talk to 100 people, 2 or 3 may be willing to.
Now, one more question you were asking for the chat window. Dr. Sasirega will be asking.
Minimum number of images required to build a suitable deep model for COVID. See, that is a difficult question, but I think the best way to kind of do this is the first thing, make sure that whatever classes you're trying, if you're trying to do COVID and non-COVID, the number of images in both classes should be more or less same. That is number one. Number two, I would say if you are trying to use some of these deeper convolutional neural networks like a ResNet 150 or a DenseNet 121 or anything like that, I would say you would need a minimum of about 150, 200 images of each, with at least each image being some 225 by 225 pixels. Because if you look at a ResNet, it has at least 1.5 million parameters. So with 1.5 million parameters, you at least need 1.5 million pixels, degrees of freedom. Otherwise, it will only overfit. So the short answer is there is no good answer. Of course, as many as you want. But if you have less than 150, 170, I would say don't use those deep architectures. Use simpler architectures. Use like VGGs and things like that. Don't use those DenseNet and ResNet and Inception type architectures. Hopefully that makes sense.
Any other?
Sir, thank you, sir. This is Atreya, sir.
Yes.
Sir, thank you for the answer, sir. I need 2 more clarifications from you,
sure,
sir.
Please, go ahead.
Sir, one thing, in some literatures, researchers are concluding that the raw image could be fed to the deep model, no need of dimensionality reduction or feature extractions. Could you share your perspective, sir, in this?
Yeah, the point is generalization is very, very difficult. So I don't have a problem with doing that. But if you are feeding just images to neural networks, I would rather have you check the interpretability of those models. So my thing to you will be, if you are trying to do that, use at least something like SHAP or LIME or something to see what is that model learning, and whatever is it learning, is it clinically valid? Because otherwise what happens is, on some test data sets you will get excellent results, but when you go into the field and actually try and generalize, the results will be very bad. That is the problem. The problem is, make sure use something like, you're familiar with some sort of gradient activation or LIME or SHAP or any one of these basic interpretability methods. So use those basic interpretability methods. And if you really want to do it, use something like deep Taylor visualization, okay, which is probably the state of the art. And then, because for example, if you do a deep Taylor on a convolutional neural network, it will give you the areas, the pixels which are contributing to its decision. So once you have that, take it to a clinician and ask him, are you also looking at these areas only while you are making a decision? And if those areas are very, very different, more research is required to say that this neural network is still learning the right thing. I'm not saying it is wrong, but more research will be required than putting it into production straight away. Because here it's people's lives. Misdiagnosis is a big problem. You cannot misdiagnose. If it was just cats and dogs, then fine. Hopefully it made some sense again. That's just my thought.
Sir, do we need to pre-process the image, sir, before feeding to any, before feature extraction or further analysis?
Yes, you always have to, because see, at the end of the day, every great technique in the world, all that it does is, see, all that you have is values between 0 and 255. And all techniques at the end of the day will be something to do with intensity change only. Okay, whatever you talk about, at the end, it will be about intensity change. So I would rather normalize those. What do I mean by normalize? I will get those numbers between 0 and 1 or between some smaller interval, so that errors like these, errors due to, because otherwise what will happen is the difference between, let us say, some pixel value is 25 and some pixel value is 200. The difference between 25 and 200 is so high that another pixel value might have a value of 10 and this pixel value may have a value of 25. The difference between 10 and 25 will be lost in importance compared to the difference between 25 and 200. Whereas the difference between 10 to 25 also may be significant. So ideally, even if you are feeding it to a neural network, I will normalize the pixel intensity values to something like 0, 1. At least that is the minimum pre-processing I will do. Of course, if possible, I will do the others also, like some amount of cropping and cutting and some amount of data augmentation, rotation. All of that also we will do. But at least normalization, though, definitely I'll do. You understand my reason why?
Sir. Thank you, sir.
Thank you.
Yes, sir, I understand. Thank you for the reply, sir. And also, you have shared your experience with us. It's really useful for starting the research in this area, sir. Covet.
Yeah. Please do. This world and India requires more and more people to research. Unfortunately, in India, it is very difficult to get this data. I would suggest, because you are an academic institution, explore foreign academic institutions. They may be far more forthcoming.
Okay, sir. Thank you, sir.
Thank you.
Sir?
Yes, please.
Sir, one more clarification, sir.
Sure.
Consider pneumonia as well as COVID. In case if a person is having both. Hello?
Yeah, right now we have not explored that option. You're right.
Okay, sir. If a person is having some other respiratory diseases too, including COVID, pneumonia, and such kind of diseases, will it be able to use an algorithm for differentiating, finding?
I don't know. Very good question. I don't know what happens if you take somebody from asthma and they have COVID. Then what happens? Okay, I don't really know.
COVID patients are more likely to get pneumonia, like that. Some researchers.
Yeah, exactly.
So if they are having associated diseases like pneumonia, COVID, and some other respiratory diseases too, then how to differentiate and how to find how the X-ray image will be looking like? Do you have any idea, sir?
No, I don't. This could be research we have to do. I don't know. I have not worked on this, so I don't really know. See, right now there is another project that I'm working on where probably if one of you is interested, we can collaborate. Is audio analysis, basically cough and vowel sound analysis between COVID and non-COVID patients.
Okay, sir.
So that may be because instead of looking at a lung image, we were thinking, this was not my thought, this was another doctor that I was working with who gave me the idea that can we actually go with the sound that is produced?
Sir, I'm having a respiratory disease, sir, like having too much cough and those things, but not COVID positive. So I used to think that what is the difference between COVID positive patient and a normal cough and between pneumonia? What will be the difference? Like that, I used to. So that is what the question I'm asking.
Yeah, I know. Unfortunately, I'm not a doctor, but
through X-ray, how can we differentiate and how can we find? We can also do that, no, sir.
Yeah.
This will be also be a different research area.
Yeah, absolutely. See, with COVID, frankly, we still don't know much now. We are still learning. Every day we are learning. We don't know. So no question is a bad question.
Okay.
we have no idea. Yeah. Exactly. COVID with associated. How will we do it? Yeah. I don't know. I have not worked on it. But interesting problem. Maybe we can solve at some point.
Thank you.
Thank you.
Anybody there asking some question related to computer vision, COVID, machine learning, and artificial intelligence? Final
Okay.
year students. Final year students, so many things are moved to image processing, go to with the computer vision projects like that, tie up with so many machine learning aspect using Python or any other machine learning algorithms. Okay, you can go to ask for this because chief data scientist. This is the best opportunity. Students can go to ask for any doubts related to machine learning things, whatever anything.
Yeah, please do. Please ask anything. Don't worry about it. There is no wrong question. There can only be a wrong answer. So, questions cannot be wrong. No, only the answer can be wrong. And if I don't know the answer, I will tell you and I will share some material if I can find it. But don't worry. I worked in this field long enough. Mostly I'll know some little bit about most of things. So you can just ask. Don't worry. Don't feel shy and all. I think you're all feeling shy about this or that. Don't feel like that. There's no point. I also used to be like you only. So don't worry. Just say something. Okay. Thanks, guys.
Professor? 19 points. Anybody
Okay,
ask any questions? Wait for 2 minutes, sir. Okay.
Yeah.
Thank you for this wonderful talk about this COVID X-ray analysis using computer vision, and also to be linked with all the mathematical UMAP and then all the type of GitHub projects, especially dimensionality reduction, topology data analysis, and then linear cross entropy. All that is simplical complexes, and then all the type of what is real-time aspects of DMD modes, and your future work is also be Koopman operators. It's also be focused. Thank you, sir. Thank you very much. It's wonderful to link with your sharing for your experience, and also thank for our Vice Chancellor, Professor P. Kolandeval sir, to got this type of wonderful opportunity. And also we thank with Professor K. Thangavel sir, Register in charge, and also our head of the department of our computer science department. Thank you, sir. This is the backbone of this conducting this online training program. And also thank for our faculty members, and also thank for our PG Extension Center faculty members, and also thank for our PG students, as well as research MPhil research scholars, PhD research scholars, and outgoing doctorate scholars. And also thank for our PG Extension Center students, scholars, and thank for our office people to conducting this online training program. Thank you for all. Thank you, sir. Thank you.
Okay, thanks everybody, and thanks. Good. It's good to talk to students and teachers and everyone. Yeah, thank you. And feel free to connect with me if you need anything more. Yeah.
Sure, sir.
Okay.
Sure, sir. Thank you.
Thank you.
Thank you.
Bye.